Okay, in this video I'm going to talk about linear regression, and the goal of this video is actually to give you a full hands-on grip on what linear regression is. Basically, mostly for different models, we will be using built-in functions or available models inside Scikit-Learn. But it is always good to just go through one or two models from scratch to get a look and feel that in Scikit-Learn what kind of implementation is there and how people actually implemented that. So in this particular video, I'm going to give you an example of linear regression, although we will code that in Python as well, but we will not be using Scikit-Learn for this. We will be building our own linear regression model from scratch. So let's start. This video will be having some mathematics in it. I will try to minimize the content of mathematics as much as I can, or equivalently I will try to make the intuitive sense of each and everything that I'm going to write. So let's start. Let's take a very simple example. Let's say our feature is only one. X is our feature. Let's say only one feature. So the total number of features is just one, and Y is some target. So let's say this is feature and this is the target. So this is xi, ith feature, and the ith target. And let's say we have some data, the ith feature value, let's say, is 2, and the target is 5. Ith feature value is -3, and another sample has feature value -3, and the target is -2. Maybe the feature value is 7, and the target is 5.9, and so on. So we want to build a model that maps this feature to the equivalent target, at least for the training data. And for this particular example, we will be using synthetic data just to get a look and feel of what regression is. So linear regression means we are going to build a linear model for it. First of all, let's see what our function is. So our y hat for ith example, which is our prediction, relies linearly on our ith example, which means xi times some parameter a and some other parameter which is b, because that's the linear model. If we do not allow this b as a parameter, then we restrict our model to always pass through the origin in the feature space and do not go away from the origin, which in some cases may be harmful. So it is always good to allow this b, and it is sometimes called bias and also called intercept. Either way, so that's our model. We want to find out a and b, and we have a lot of data points to build this a and b, and our belief is, our hyperparameter is that the mapping between x and y is really linear. So how can we do that? Let's see that in detail. So I'm rewriting the same equation. I want to find out a. I am available with xi, which is this, and plus b, and that is equal to yi. Yes, I can rewrite this equation in matrix form. If you remember, or if you know the matrix multiplication, if I write this xi1 as a row vector or a matrix, and if I write this as a matrix, let's say a and b, then the result might be yi as a matrix. Yeah, so that's an array xi, and that's these are the parameters that we really want to find out, and that's the ith data point. This matrix multiplication happens like so. This xi multiply with a, this one multiply with b, and you add them up, you get the same equation back whenever you want. So let me rewrite the equation as axi plus b is equal to yi, and its matrix form is xi1. 1 because we want this b to be added in a is equal to yi. Yes. Now this is for ith data sample, ith example. What we can really do is what we can really do is we can have for example this this first data sample as x1 1 and AB equals to y1. Then we can have second example concatenated down there, because the same equation has to follow, the same equation has to hold for the second example as well. The same equation has to hold for the third sample as well, and so on. Yes, x n and 1 and yn. So at the end of the day, we will be having this two-dimensional array. Let me call that array as x. This particular array as x. X will be a two-dimensional array with n rows and 2 columns. And we will be having this array, which is array of parameters. Let me call them as A. And that is equal to this right side array, which is called y. And the y basically is n by 1, and this a is 2 by 1. So the goal now is really to solve this equation, x. Let me write the parameters in the different colors. X a equals to y. So how can we solve this equation? First of all, we will use the training data to build this matrix X. We will use the training data to build this vector Y, and then we will be using a linear algebra library from NumPy, and we will solve that using an optimization routine called least square optimization. Remember, our error function initially was minimum squared error. So here we will be using the least squared error solution that I will be using as a black box from NumPy. I will not be going into the details of least square, although we have another course, mathematics for data science, in which we explain all these algorithms in detail. So to get a look and feel of the underlying theory about these algorithms, do enroll our course, mathematics for data science. Okay, anyways, so that's about it. Once we have this data matrix X, we have matrix Y. The next thing is to solve this equation for A. Once A is needed, we are done. So let's go into the Jupyter Notebook, our friend, and try to solve this. Okay, let's continue our discussion, and let's code this linear regression model that consists of just one feature in Jupyter Notebook, and let's get a look and feel of what how linear regression can be implemented. So first of all, let's generate some data. I guess we have already generated some data previously somewhere in this notebook. So why don't we copy that code just to generate the data? Yeah, here, I guess. That's the data. So let's pick this code and see what the data is. Yeah. So that's our data. So we generated some data. This data is the actual relationship here is no longer linear. It is some quadratic expression. But let's say we want to fix. Why don't we actually use a linear function? Why don't we actually generate a linear data? Let's say that's the data. That's a line on a line. We are available with a lot of X and the corresponding Y. Let's see the shape of X and shape of Y. And now we want to fit the regression model that actually helps us finding out this function or the line inside the parameters. So X dot shape, that is this, that's X. And if you see Y dot shape, that is this. Now if you go back, we need our X matrix to be in the form that all the features, they should be here, and then a 1 should be appended right there. So how can we do that? Let me use is there any function like ones in NumPy? Let's say np dot, maybe there's a function with ones, np dot, do we have NumPy loaded already? Or we don't? Yeah, NumPy is loaded, already loaded. So why is it not running? I just want to see whether we have ones function or not, because I want to concatenate this x with ones. np dot, it is not showing me the let's check whether there is some function np dot ones or not. Yeah, there is. np dot ones, we have to give the shape, and ones function is there. There's an example as well. That's how we can do the ones and all that stuff. So yeah, let's use this ones function. Let's say we have a variable on as np dot ones, and we give the shape inside. The shape is really x dot shape or size, maybe in this particular case, comma 1. That's our, so if we see this on, which is just the ones, these are these values. Now let's concatenate let's concatenate this on1 and x. Let me generate a matrix x. Let me call it as x2 as np dot h stack, horizontal stack, np dot h stack, and what we do inside is we stack the x and on, and we copy the result in, oh, there's an error. All input arrays must have a number of dimensions, but the array is 0 index and dimension 1 and stuff like so. Let me see what is happening. Let me just see what is happening. Maybe there is some problem. So this x dot shape is like this, and this on dot shape is like this. So this on dot shape, it is basically in two-dimensional form, but this x dot shape is no longer in two-dimensional form. Maybe we should use a new axis property for this. Maybe we should use that x like this, and everything, and np dot new axis, and this may help. Yeah, it does actually, and that actually allows us to concatenate both x and x2, both x and ones. Now if we see this x2, it is basically an array of the form that we really needed. It has all the features, and then right side all the values y. We can also convert this y to new axis as well. What is the y basically? Y, we already know it is the shape of y, we already know it is this. Okay, now where x is ready, y is ready. If we really want to convert our y with new axis, we can do that as well. Y is equal to y that with np dot new axis, and that's our y now. If you now see the shape of x2, that is this, which means there are 20 samples. The first column is the feature values, and the second column is really all the ones, and all the ones because we have created this. If you see here, we have to create the matrix in a way that the second column must contain all ones, and the first column all contains the feature values. Yeah, and y is just array with all these target values. Once we have this, we are now able to solve this x, y, and stuff like so. So yeah, let's go. Let's see the shape of y now. Y dot shape. It is yes, consistent. Now I'll be using least square function from NumPy, linear algebra library, and that's in the optimization function that I was talking about. The optimization that actually helps us finding out the parameters. So let me see how to use that first. np dot linear algebra library dot lstsq. How to use that? I just forget how to use it. Let's see. Oh, there's a help inside Python. If you want to use this function that returns a solution to a system of this particular form, ax equals b. So yeah, then why don't we give these values x and b there, and we just try our best to get the values. So what we really do is the following. So a, that is our result, that will contain two numbers, is np.linearalgebra.lst_sq, and we pass x2, that's our data matrix, we pass y, that's our result. So it's saying that recondition parameter will change from default to this. So there is a recondition parameter. We can set that recondition parameter as well. Re-arcon parameter, and that parameter, maybe we set that to 1, and we just still that's to keep using the old explicitly pass -1. So maybe we just go okay -1 and just get rid of this warning, although having warning is perfectly okay. Let's see what a is. A has two values. It's 4, 3, which means the values are basically so 4, 3. These are the two values in A. Let me see the type of A here, what kind of array A is. So A is a tuple. It contains a lot of things. The tuple because the return value, return parameters, if you again see np.linearalgebra.lst_sq, if you see that the documentation of this function again, you will see the return parameters are actually the coefficient matrix, then you have b, which is the dependent variable values, then you have recondition, and there are a lot of things that are returned in a tuple. So yeah, so no. These are parameters, these are return values. So the return values are actually the solution, the residuals, and the rank. What is the rank of the matrix? And these are mathematical terms. I don't want to go into the details, but all am I saying that if you want to get the result, actual coefficients, all you need is to just see the that's the result. That's our coefficients. And guess what? Our coefficients here are 4 and 3 that we estimated, and the actual coefficients were also 4 and 3. These are the actual parameters. This is how the data is generated. That's the actual relationship between x and y, and we just estimated it. We just estimated, and it becomes 4 and 3. If we now, for example, plot, like in as a line here, then let me show you that plot. This is our so what is the prediction? What is the y hat? Let me call it a y hat or y prediction on the test, on the training data. So on the training data, the prediction is a 0, 0, which is the 4, multiplied by x plus a 0, 1. These are the predictions, and now you can plot your predictions. That's how you, if you remember, when we call model.predict function, that actually does this thing, and this least square function that we call, that actually resembles to model.fit function of built-in values that we did earlier. So now if we have this predict, now let's plot. Now let's plot the actual data, and let's plot the predicted values, y predicted. Let's say color is equal to red. Let's do that, and you can see we actually are predicting each and everything perfectly. That's because the data was not having any noise. It was perfect data. We can always find out a line and all that stuff. Now let's play with this code. Let's generate the data in a different way. Now let's say the data has noise. Let's add a noise in the data. Let's say the data has noise. np.random.randn randn, and let's say we are just adding as the noise as, let's say, x dot size. X dot size. So let's say we are adding this noise, and now you can see the data is not that linear. It is just going above and below. Let's increase the magnitude of the noise. Let's increase the magnitude of the noise. Let's say we have data with this noise. The targets are just noisy, which basically happens in the real scenario. Now this is our data. Now let's say we still believe that the actual pattern, the actual basically the relationship between x and y, let's say that is still linear. And even in the presence of noise, let's basically try to fit the model here. Let's say again we have x2 like this, and that's x2, and we move to y dot shape. These are all the codes that we written earlier. And now let's run this lstsq, the actual, that's tuple, that's again open up, and now let's see what are the parameters that we estimated. Now the parameters that we estimated are a little off than actual 4 and 2, and the reason being there was noise in the data, and that is the best line that actually it predicts. So if you now see, this is the original data, the blue dots, that's the original data, and that's the prediction that we came up with. And now because we have the coefficients, we have the parameter values now we have the parameter values. Now we can predict on any data point, that is whether seen or unseen or stuff like so. So I just wanted to go through over this linear regression code from scratch, just to give you a look and feel that all these functions that you're using from Scikit-Learn as built-in, if you want to implement them, they are not really that hard. You can do that from scratch as well if you want to do that. So yeah, so I end this video here. Why don't we plan to implement our own classifier, at least one, from scratch, and why don't we think to build our own cluster or k-means clustering algorithm, at least from scratch for once, and then we will just move to Scikit-Learn after believing that if we want to implement those by ourselves, there are ways to do that. So in the next video, I'm going to actually build a classification model from scratch without using Scikit-Learn, without using any built-in model from Scikit-Learn. I will use a very simple one just to convince you, but we will be building it from scratch in Python. So hope to see you in the next video.